Yeah, I hope the screen is visible.
Yeah, it
So,
is. It is.
okay, thanks. So I basically want to talk about what are called minimal models, and this is going to be pretty much independent of the lecture I gave last time. But you'll see the connections between the last lecture as well as the connections of this with the subsequent lectures. So one point that I want to mention at the outset is that I've added one more reference, and this was I was in fact thinking about whether to put it or not, and then Shrikant suggested this, and I think it's a good reference. It's a book by Felix Opria and Tanre called Algebraic Models in Geometry. And so, although it may not have all the specific details of the various constructions, it does have a ton of examples covering various, like places where rational homotopy theory finds use. So I've added that book in the reference. You can have a look at it. And for this lecture, I'm primarily going to also make use of the book by Griffiths and Morgan, Rational Homotopy Theory and Differential Forms. Okay. Okay. So let's again start with so let's start easy, and then I'll sort of build up with examples and so on. So we're going to start by defining what's called a DGA. And for those of you who know what a DGA is, just bear with me. We're going to start doing interesting things. So a DGA is nothing. It's a short form or abbreviation for differential graded algebras. Okay. So formally speaking, our algebras are going to be over fields. You can talk about algebras over rings, and you might encounter some of these things in other lectures. So for us, a differential graded algebra denoted by A comma D, so this is a script A, is a graded vector space over a field K. For the most part, this field K is either going to be Q or R in our examples, but as of now, it's just a field K. And this A is a graded vector space, means in our setting we're going to assume that these are non-negatively graded. So basically elements of degree k are going to be the elements of a to the k, and because I'm going to talk about cochain complexes, I'm writing the degree as a superscript and not as a subscript. Okay, so a is a direct sum of a to the k, where each ak is a vector space over the field k, and there is a differential, hence the differential in the differential graded algebra terminology. So this is a map D, and we all have seen plenty of such examples. This D should square to zero, meaning if I compose D twice, it's zero. And D has the property that it's a degree 1 map, meaning it takes elements of degree k to elements of degree k plus 1. Okay, and all the maps that I mentioned here, the map D, the multiplication, and all these things, they are obviously k-linear maps. So that goes without saying. So I haven't mentioned them here, but that is automatic. I mean, or it is implied implicitly or otherwise. So, and we have a multiplication m. Usually we just discard the m and we'll denote it by the usual dot, or just concatenate letters next to each other. So it takes an element of degree k and an element of degree l, and the output is an element of degree k plus l. So the multiplication map should be thought of as a map of degree 0. The differential is a map of degree 1, and the differential should satisfy the Leibniz rule. And what does the Leibniz rule say in this case? It just says that d of x times y is dx times y plus, there's a sign, and it's minus 1 to the degree of x times x into dy. So again, in this equation, I'm assuming that x is a homogeneous element of some degree k. Otherwise, I just break it up into homogeneous terms and then I use linearity. So I can always expand using this rule. Okay. And this sign is there essentially because D is a map of degree 1, and it's essentially moving over the element x, which is of degree mod x. And so you pick up a factor which is minus 1 to the sign of the degree of x times the degree of D, which is minus 1 to the mod x. Okay. And as you can expect, a DGA is going to be called commutative. Uh, so some authors call it graded commutative, but in our setting, everything is graded dash, like graded adjective anyway. So commutative means that if I switch x and y, then I have to basically change by a sign, and the sign is minus 1 to the degree of x times degree of y. And you have already seen examples of such things, namely differential forms where something exactly the same happens, except that instead of dot, now you have a wedge product of forms. So that is going to be an example we'll talk about. So we are going to be talking about commutative DGAs. So it should be a differential graded algebra which is commutative. Okay. And I haven't said it here, but it's assumed throughout the talk that the multiplication M is an associative map. Okay, so my algebras are associative as a blanket assumption, and often they are going to be DGAs, and even more often they're going to be commutative DGAs. Okay, okay. So this is a very basic definition. So let me give you some examples, at least the examples that will be relevant for us. Okay. So the first one, as I was alluding to, is differential forms, right? So you take a smooth manifold M, you look at the DRAM complex of smooth differential forms. So essentially they're generated by the smooth functions, C0M, and then you take D of that, and then you basically, which gives you the one forms, and then you take D of that, those are the two forms, and you start taking wedges and so on. So in some sense, it's generated from the functions. So we all have seen this in differential geometry. This is a commutative DGA over the reals, and here the multiplication is given by wedge product of forms, and the wedge product of forms is commutative, meaning it's graded commutative in the sense we saw earlier, but as I said, I'll still call it commutative. Okay. So this is one example of a commutative DGA. So often I'll be abbreviating even this and calling it a CDGA just to save space and time. Okay. So CDGA is short for commutative differential graded algebras. So the next one is something that you have been seeing singular cochains. You have seen singular chains. So singular cochains are defined to be the duals of the singular chains. And so for any topological space X, you can look at the singular cochains with coefficients in some ring R. Here you can take it to be Q, for example. And this delta is the co-boundary map acting on the cochains, right? And so when you calculate the kernel mod image, you get the cohomology of X with R as your coefficient ring. So here you have a multiplication which is given by the cup product, right? So the Alexander-Whitney product. So you have a differential graded algebra, you have a multiplication, the multiplication is associative. The point is the multiplication is not commutative, because if you have seen singular cochains and singular cohomology at least once, one of the first things you check is that from definition, you can show that alpha cup beta is not equal to even up to a sign beta cup alpha because of the asymmetry of how the cup product is defined. So this is an example of a DGA which is not a CDGA. Okay. The next one is trying to rectify this issue by basically passing to the singular cohomology. So you take the singular cochains, you take its homology. So what you get is the singular cohomology, kernel mod image, and you can treat that as a differential graded algebra, just that there's no differential because you have already taken the homology. So for every space X, you can take, for example, its rational singular cohomology, and I'm denoting that by, so whenever I put dot here, this dot is actually a graded sum of H0x, H1x, and so on. Same here and same here, right? So I can think of this as a differential graded algebra. The differential is just zero. So effectively, I can always put the differential to be zero. So those two conditions are vacuous. And then it's a graded algebra. The algebra arises because the cup product induces a product on the singular cohomology. And this is now actually going to be commutative because the cup product is homotopy commutative. This is one usual computation you show, that alpha cup beta plus minus beta cup alpha is, I mean, if alpha and beta are co-cycles, then this thing is equal to the co-boundary of something else. Hence, in cohomology, it indeed is commutative. So this is an example of a commutative graded algebra where the differential is simply zero. Okay. And then we have this example where again, I'm not going to talk about the differential, meaning that the differential is going to be set to zero. So you're simply talking about a commutative graded algebra, and the adjective free here means that your algebra is basically generated freely up to the relation of commutativity. Meaning, I want my A, the algebra A, to be of the form. This is the symmetric the symmetric powers of the even part of V. So V is a graded vector space. So V will have, let me show the full thing. So V is a graded vector space. So V will have the even parts and the odd parts, meaning you look at V0, direct sum, V2, direct sum, V4, direct sum, V6, all the way. So these are the even parts of V, or the elements of even degree. And then you have V1, direct sum, V3, direct sum, V5. These are the odd elements of, or elements of odd degree in V. And so whenever I talk about the free commutative algebra on V, I basically mean that the only relation that I'm allowed to impose is that x times y is -1 to the mod x mod y, y times x. So if I switch two even degree elements, it doesn't change anything. I mean, there's no sign. If I switch to odd degree elements, I get a minus sign. Okay, and so hence for odd degree elements, you basically get that x times x is minus of x times x. And since we're working over Q, for example, you get 2 into x times x is 0, so x times x is 0. So you get the exterior algebra on the odd elements and the symmetric algebra on the even elements. So this is going to be often denoted by wedge V. But this wedge is not to be confused with wedge of V even or wedge of V odd. I mean, this is just a notation, but it means exactly what I explained here. Okay, so this is an algebra because all you're doing is just multiplying these kind of tensors. Okay, and the differential is 0. So these are four models which will appear somewhere down the line. So, okay, are there any questions? Okay, so let me talk about, so what are we after in this thing? So I'll get to what minimal models are, but before that, the point here is, see, one issue that you sort of see is that the singular cochains is a DGA which computes the cohomology, but it's not commutative. And the singular cohomology is, of course, commutative, and it is the cohomology. So obviously, it's computing the cohomology. But there is something called the commutative cochains problem, which was in some sense, the genesis of this rational homotopy theory, one way or another, either by Quillen or by Sullivan. So there, you're trying to find nicer commutative DGA models for a space, in the sense that these commutative DGAs would compute the singular cohomology with Q coefficients, for example, of the space, and it should also have some other properties, namely that if Y is a subspace of X, then there should be a restriction property from the assignment from X to Y and so on. So it turns out, due to Steenrod operations and so on, that you cannot expect a commutative quotient problem to have a positive answer with integer coefficients, but you do have a hope over Q. So that is sort of the basic history behind why, for instance, Sullivan was trying to construct such a model. But to jump ahead, what we are going to talk about is this model. So if you forget the context for a moment, the aim is that for each topological space, we want to discuss a construction of a CDGA, a commutative differential graded algebra, APL of X. And this is going to be constructed out of certain kind of differential forms with rational coefficients. Okay, so this is what Sullivan constructed. And then after we talk about this and see some examples, we'll talk about what are minimal models associated to topological spaces. Okay, but this is sort of the first goal, that we want to construct this thing, which is in some sense a nice model computing the cohomology of the singular rational cohomology of X. But this is constructed more like a hybrid, that you're trying to use differential forms, but your spaces are not manifolds. But then you still try to use the fact that you can reconstruct a space by its singular simplices. And so you try to combine these two in order to construct something which is, a bit of a hybrid, because the differential forms are automatically commutative. The singular cochains are not. And so you try to come up to a nice, intermediate place where you can talk about both in a controlled way. So yeah, so we are going to, so the next few slides are going to be devoted to discussing this construction APL of X. The first, of course, being what happens when X is a simplex. Okay, so the n simplex, the standard model is this one. It is the convex hull of the basis vectors in Rn plus 1. So this should be the usual math BBR. So there's a small typo. So del n is simply going to be T0, T1 dot Tn such that summation Ti is 1 and the Ti's are between 0 and 1. So this is nothing but the convex hull of the basis vectors of Rn plus 1. And this is an n-dimensional simplex. So what you could do is you could consider the restriction to this simplex all forms in Rn plus 1. So Rn plus 1 has the usual forms, but now you restrict your choice of forms in Rn plus 1 to, so by forms I mean differential forms. Of the type, this is a finite sum. There's some function phi, which of course will have a subscript as a multi-index because this is going to be a J form. So it's dt I1 wedge dot dot dt ij, and this is going to be a function of t0 through tn. Okay, but I insist that these functions are not arbitrary smooth functions; they are polynomials in the ti's with q coefficients. Okay, so the ti's are of course just coming from the usual. These are the local or the global coordinates in Rn plus 1. So I want these functions to be polynomials in the coordinates of Rn plus 1, but with rational coefficients. And then these are the usual dxi's. I'm just calling them di's. So we basically look at all such forms and then we restrict them to the n simplex. Okay, and this will form a CDGA because it is sitting inside uh, the space of forms. You're just restricting yourself to certain kinds of forms, and we'll denote this by a PL of delta n. Okay, so PL for piecewise linear, and we'll see in the construction uh, why this like piecewise gluing condition appears. So right now this is the notation. Okay, so this is just forms of this kind, and this is a CDGA. So you can check very easily if you just compute the cohomology of this. This is concentrated in degree 0, which it should because delta n is contractible. It is homotopic to a point, and so the usual cohomology is that of a point which is concentrated in degree 0 and it's going to be equal to q. Or if you do it with any k coefficient, k to be a ring, then you'll just get k. Okay. And if you have a face of the n simplex, a typical face of codimension 1 looks like when you set one of the ti to be 0. You can set several ti's to be 0. So if you have a face of codimension n minus k in delta n, I'm denoting that by delta k, then there is a very natural map of CDGAs which goes from this CDGA associated to delta n to this CDGA associated to delta k. And what does it do? It basically is the restriction map. So given any form on the big simplex, you restrict it to the face, and that's still a form on the subsimplex. Okay. So we have these two properties for this particular construction. So this is a very simple model, but we're going to make use of this and talk about first a model for a simplicial space, and then what happens for a general topological space. I mean, how do you construct the analog of this APL for a general space X, and then talk about its properties that are key to the discussion. All right. Okay, any questions? All right. So, okay. Yeah. So, if I start with a, so, okay, before
Can
I,
I ask a question? Sorry.
sure.
Um,
We want
is there a map going the other way? APL of delta n to the APL of delta n plus 1. Like, can we also get that? Sorry. Yeah. So
no, no. What is your question? You want a map from?
you got from the higher simplex to the lower simplex, delta n to delta k. Can we also get something on the other direction?
Yeah, yeah, you can. So that will depend on the map. So like this is like a face map, right? And then
Yes.
if you have a degeneracy map, then you can get the map the other way as well. Yes.
Yeah, yeah, yeah. I wanted degeneracy.
Yeah, yeah. So I'll talk about that. That will come. That's going to come up
Okay.
probably the third slide after this. Yeah. So this is essentially, yeah. So this is like an iterated face. So you take a face of a face of a face, and then this is going to be one such, right? So this delta k because it's going to be a codimension n minus k face. So every such face map will induce a map from APL delta n to APL delta n minus 1, and then we'll see that the degeneracy maps will go the other way. So, I mean, does that answer your question?
Yeah, thank you.
Okay.
Yeah.
Yeah, so before I talk about a model for simplicial complexes, I want to just point this out, because if you're reading, say, for example, this algebraic models in geometry, that book, then this is how they start to define this, which might seem a bit less geometric than the definition I gave you, but it's the same. So essentially, then one could abstractly define APL of delta n to be the CDGA, which is, just think of this as a formal thing. And this might resonate well with how you construct these like formal, the scalar differentials in algebraic geometry. You just basically construct the free commutative. You first look at the vector space where V0 has n plus 1 formal basis elements, T0, T1 up to Tn, and then you formally call a vector space V1 to be generated by elements dt0 dot dot dtn of degree 1. So if you want, you can call them y0 through yn. I'm just calling them dt0. So this is your v0, this is your v1, and your entire v is v0 plus v1. And so this wedge is nothing but the free commutative algebra generated by v, which is wedge of v. And there you're and then the differential there is pretty clear. The differential is going to take the ti and map it to dti. So d of ti is literally this variable dti, and since d square is equal to 0, we put that d of dti is 0. Okay, so it's clear why this is a differential graded algebra. And then you mod out by this, and this is sort of already foreshadowed by what you're trying to do. So you're trying to work on the simplices, which are constrained by the equation summation ti is equal to 1. But because summation ti is equal to 1, you're formally allowing yourselves to differentiate this relation, and then you get summation dtj is equal to 0. So you have to mod out by this. But then if you do that, you'll see that what you get is exactly the algebra that like I talked about uh, in the previous thing. So you can also start by defining it this way as an abstract CDGA. Okay, so now if you want to do the same thing for a simplicial complex, there's a very natural way to do things. A simplicial complex is essentially you have a collection of simplices which fit together very nicely along their faces in a very controlled fashion. So what you do is you basically take the APL of each of the constituent simplices, and then you insist that you're only going to talk about collection of forms, one for each of the simplex, such that whenever the simplices are glued along a common face, the forms restricted along the common face should agree. It's just that, right? So I declare APL of K to be the CDGA of piecewise polynomial forms with Q coefficients, and it's piecewise because it might be one kind of a polynomial form on one two simplex and another one on another two simplex, but they might agree on a common one simplex, which is a face of the two triangles. Okay, to be the collections of all. So the set is a collection of all such omega, where what is omega? Omega is itself a collection of omega sigma. So omega is a polynomial form with Q coefficient, one for each simplex in K, and they should be compatible. So compatible means what? It means that if tau going to sigma is an inclusion of a face, then the assignment to omega, if I restrict to tau, should be the assignment for tau, which is just another way of saying the pullback of omega sigma is omega restricted to tau, or the assignment of the form at tau. Okay, this is just a compatibility condition. So you declare APLK to be the collection of all such things, and one can check that this is a CDGA. You can take the wedge, you can take D. Okay. So yeah, so the first sort of theorem which connects this with what we are trying to do is that we are trying to say that not only is this a nice CDGA, it actually computes the singular cohomology with rational coefficients of K, for example. And so this is true. So here's a theorem. It says for a simplicial complex K, you can consider the integration map. And what is it going to do? Well, I'm calling that map rho. It's going to take an element omega here. Remember, an element omega is just a collection of compatible polynomial forms. And I'm going to define a map to the simplicial cochains of K with rational coefficients. So this dot on the top means these are cochains. The simp is short form for simplicial, and q means these are taking values in q. So what does it do? So given this collection omega right here, rho of omega has to be a simplicial cochain, which means given a constituent simplex sigma, I have to give you a rational number. And what does it do? Well, you look at the omega sigma and you integrate omega sigma over sigma, and and whatever you get, that's a rational number, and that is basically this map. It's just integration. Okay? And so the point is this will induce an isomorphism uh, of so I probably should have written isomorphism in cohomology of algebras, but just I mean it's clear that that's what I meant, but just make a note of it. So the point is this is going to be a quasi isomorphism, so it's going to be an isomorphism of algebras when you pass to cohomology. So on this side, you'll get the simplicial cohomology of K with Q coefficients. On this side, you'll get the corresponding cohomology. Okay, and the proof of this, well, it's not entirely immediate, but the idea of the proof is that you basically have to show that this map is surjective, and then you also have to show that this is actually a chain map, which basically relies on proving. So it's like proving a version of Stokes theorem, which is true in this context because you're dealing with smooth forms anyway, and on a particular simplex. So it's restricted simplex, like simplex wise. But then you also need to prove a version of Poincaré lemma in this setting. So remember, Poincaré lemma says that if you have a star-shaped region, any closed form is exact. So you have to prove a version of that in this setting. And once you have those tools, you can essentially put these together to give a proof of this fact that this is a quasi-isomorphism. Okay, so it induces an isomorphism in cohomology. Okay, so this is the intermediate step. We talked about APL of simplices, we talked about APL of a simplicial complex, and now we're going to talk about APL of a general topological space. Okay, so all right. So to do that, I basically want to briefly just take one slide and talk about simplicial sets, because that is the cleanest way I can talk about without sort of writing too much stuff and letting this be a meandering sort of discussion. You will, of course, see a much more detailed discussion on simplicial sets in Rekha's lecture later. So if some of the things are not immediately clear, you can ask me or we can discuss it even then. So I'm just going to just briefly say what it is. If you have seen it, then you already know it. If you haven't, then me writing down all these relations, what a simplicial set satisfies, is not going to be very illuminating. But let me briefly say what it is. So a simplicial set is a collection of sets, script k, which is a collection of sets kn, n indexed by non-negative integers, equipped with a collection of maps. So for each n, you get these maps del i's from kn to kn minus 1, and for each n, you get these maps si's from kn to kn plus 1. Okay, so there are n plus 1 maps going from kn to the top thing, and there are n plus 1 maps going from kn to the bottom thing, right? And these maps satisfy some specific set of relations. I'll not say right now what these relations are. You'll see some of them very soon. So there are some relations saying how does del I del j commute with each other, and what kind of relations they satisfy. The relations asking what is si sj in terms of sj si, and then there are relations asking what is how do del I and si interact with each other. Okay, so there's a specific set of relations which really arises from the fact that the standard n simplices have these kind of have the dual sort of relations when you think of face maps and degeneracy maps. Okay, so that's where these things are coming from. So yeah, so we will need only a very particular example, and you might have seen this example, or if you haven't, you'll probably see it down the line. So you take a topological space X and you look at the set of n simplices. So remember, this is not the singular n chains. Okay, the singular n chains is the free R module generated by this set. So I'm just saying that if you look at the singular n chains, the basis is of that as R module is literally this set, the set of n simplices in X. And I'm saying think of this as your Kn, as a set Kn as outlined here. Then this will form a simplicial set. So what do I have to do? I have to produce for you these maps del i's and these maps si's. So these are called the face maps, by the way, and these si's are called the degeneracy maps. So I'll give you the formula. I'll let you go back and check that the formula actually satisfies the relations, at least the relations that I'll write down here. So it's just an easy, like bookkeeping sort of uh, check here, for example. So I'll define these maps. So what do I have to do here? So given an n simplex, I have to produce for you an n minus 1 simplex, right? So here you go. So again, think of a simplex, an element in Snx is nothing but a sigma, right? But a sigma is nothing but a map from delta n to x. But what does del I do? Del I is basically saying you restrict that map to the ith face. So restricting a simplex to the ith face means you just put, so essentially, uh, well, so it's the inclusion. Okay, so we'll think of it this way. So I want, so del I sigma of T0 T up to Tn minus 1, this is an n minus 1 simplex. And what should it be? You think of including this n minus 1 simplex as the ith face, which means the ith coordinate has to be 0. And the rest is the same old coordinates. And then it's sigma of that. So it's essentially the restriction of sigma to the ith face. Okay? It's just that. And similarly, Si of sigma is going to be taking an n plus 1 simplex 2x. And what do? Well, you basically do some sort of a degeneration, which is in the case of a triangle, which is a 2 simplex, you can project it onto one of the two sides, and that's a degeneration. So here, you Si of sigma acting on T0 up to Tn plus 1 will be sigma of everything else, but in the ith stage, you just add these two coordinates. So if you do it, for example, in a 2 simplex, you can either add T0 with T1 or T1 with T2. So you get two maps. Okay. So yeah, so you get these del i's and si's. So these are not just maps that you can think about in terms of formulas. These are actual maps obtained from the combinatorics of the simplex, and these satisfy these relations. Okay, that is something you can check. I mean, in this case, this is actually a very easy check. That del I del j is del j minus 1 del I if I is less than j. And this takes care of both things because I can always switch. And SI is this. And then there's one more involving del I and Sj, which I haven't written down, but you can figure it out or look it up. Okay. So this is our example of a simplicial set that you can associate to any topological space. Okay. Okay, so now we're going to come back to our setting of DGAs or CDGAs, and we're going to try to assign a simplicial CDGA. Okay, so before I say that, I mean, for people who are probably seeing it for the first time, there's nothing to be too worried about. What would be a simplicial CDGA? It would be the exact same things, except that now you're going to give a collection of CDGAs. So each Kn is now going to be a commutative differential graded algebra, which will have its own algebra structure, its own differential. And you want these maps, del i's, from this CDGA to this CDGA. And it should be a map of algebras. And similarly, you want a map of this CDGA to this CDGA, one for each I, such that they satisfy these relations. So I said a specific set of relations or equations. So these are two of them. Then there's a third one, which I haven't written down. So which again, one can check in the context. But that is what we're going to construct. We're going to construct a simplicial CDJ, meaning you have to give me a collection of CDJs which have these maps del i's and si's, and they are compatible in this sense. All right. Okay. Are there any questions with this construction? This is a very basic one, but for people who haven't seen it before, just think of it as how you write down the boundary map of a simplex and how you think of the degeneration of a simplex and so on. This is basically just that. Okay, so right, so we are going to construct a simplicial cochain algebra by essentially saying that for every n, so I'll denote it APL. Okay, this is just a name like script K. This is APL, and APL at n is going to be the piecewise linear forms on delta n. So this was the model we talked about, right? So these are the polynomial forms with q coefficients on delta n. So the nth CDGA assigned to this simplicial CDGA APL is this object. So what are the maps? Well, again, if you think about it, the inclusion of the jth phase is a map from delta n minus 1 to delta n. And what does it do? Formally, given t0 up to tn minus 1, it basically does t0 up to tj minus 1. In the jth slot, there's a 0, and then its tj goes to all the rest up to tn minus 1. So we already made use of this map when we defined the SIs and the DIs there. So you have this ij, right? So now you see that since this is a face of delta n, you're going to get a map del j, which is the induced by the pullback by this map. So this induces a map from APL of del n to APL of del n minus 1, which is either the pullback of forms or the forms restricted to the face. Okay. So this is my del j. And similarly, there's a projection or the degeneration from delta n plus 1 to, sorry, so this shouldn't be a hook arrow. So this is obviously a typo. This is just a map. This is not an injective map. So this is a projection, and in the sense that t0 through tn plus 1, all you do is at the jth coordinate, you add up tj and tj plus 1. So you're projecting this n plus 1 simplex onto a specific codimension 1 face. And again, if I define Sj, the degeneration maps to be the pullback of Pj, then I get Sj's, and you can again write down what these maps are in terms of the forms, but it will be exactly similar to what we had in the last slide. So I'll not write them down. And again, you can check that these del i's and Sj's satisfy the 3 sets of relations. We already saw 2 of them. You can also check the third. Okay. So this is basically just a compatible way of handling all the APL delta n's together. Okay. So now what do? You basically want to mimic the construction that you did for APLK. But now your space is not a simplicial complex. So what do you do? So what you ideally do is very much in the spirit of what you do for singular chain complexes and then constructing the space back from it. You basically look at any simplex into your space and then assign to that simplex a differential form, say a K form. And if you want to define you want to define a collection of K forms which are consistent with respect to all simplices, what you need is so essentially for every simplex, every n simplex in X, you have to give me a form, and the form should have the property that the forms, when I restrict to the boundary or to the degeneration, should be equal to the forms assigned to those faces obtained by taking the boundary or the degeneration, right? So it's just a whole huge thing which I've compatibility glued together. So the cleanest way of writing it is to say that you define the CDG APLX to be the morphisms, or the as a simplicial set to be the home. So this simp is basically the category of simplicial sets, if we can think of it that way. So this is just going to be mapped from S dot X, which is a simplicial set, to APL dot. So meaning that from SNX you have to give a map from SNX to APLN, and these assignments should be compatible with the del i's here and the del i's here and the SI's here and the SI's here. Okay. So this is just a clean way of writing things. All it means is the following, and this is what you can take home if you like more concrete things. So a Q form omega is not going to be a form on X because X is not a smooth manifold, but a Q form omega in this notion is going to be an assignment which assigns to each singular n simplex sigma an element omega sigma, okay, which is in here. Okay, so this is an element of APLN, and the top Q stands for the fact that this is a Q form. So it's a polynomial form with with capital Q coefficients of degree K, of degree little q as a form, and it lives in the n simplex. So for every such n simplex in X, which is a huge set now, you have to basically assign one such element. This is an actual form, and this collection should be compatible in the sense that if I take del I of omega sigma, that should be omega assigned to del I sigma, And if I take SI of omega sigma, that should be omega assigned to SI of sigma. Okay, so just that. So this is exactly what we did in the simplicial complex, except that we had finitely many simplices because the space was built nicely out of simplices. If you are talking about a say a finite simplicial complex, okay. So this is the generalization of that. So this is it. It turns out this is a CDGA, and this is the one we were talking about at the beginning. That for every space X, you can construct a CDGA. But now I want us to actually show that this, in fact, computes the rational singular cohomology of X. But we'll talk about that later. So, are there any questions with the construction? So yeah, so for those who are used to this language, you can take it to be this. For those who are used to more concrete things, I mean, they are the same thing. Okay, this is just a way of writing less, so you write it this way. But compatibility precisely means this. Okay, so all right. So a few properties, and again, I'll probably just briefly mention justifications for some of them. I cannot definitely talk about this thing. The first property is that this indeed is a good model in the sense the cohomology of this CDGA is the singular, the rational singular cohomology of the space X. So that's the first point. The second point, which is perhaps more interesting to people who are into manifolds and stuff, if you have a smooth manifold, instead of taking all chains, you can actually go back to the intermediate step. You can choose a smooth triangulation. So you can assume that M is a simplicial complex because you can choose a triangulation of M. Okay. So this probably goes back to Whitehead or maybe even earlier, this result that any smooth manifold is triangulable. So now you can consider these maps. So I'm going to write down several maps at the same time and take some time to pause and explain what these maps are. So you'll see 5 objects here, okay? And so the first thing here is take the usual APLK tensor with R over Q. All right. This one is what we encountered earlier. This is the singular, the simplicial cochains of K with coefficients in the reals. This one is the usual singular cochains. So I'm just putting K here because I'm thinking of M as a simplicial complex. Same here. This is just M as a topological space. So this is the singular cochain complex. What is C dot infinity? This is basically the smooth singular cochains. So what you do is you basically don't work with usual chains, you work with smooth chains, and then you take the dual of that. And so this is somehow more amenable to geometry and analysis. And so there's a map from here to here, which is the restriction map. And then there's an obvious map from the differential forms to this thing, which essentially is by integration, okay? And the claim is that all these 5 arrows are quasi-isomorphisms. So this map is a quasi-isomorphism because essentially this is Stokes' theorem along with Meyer-Vittorius argument practically. You just prove it for nice contractible open sets and then you patch them up over the intersection and the union, assuming that M has a good cover. So this is that. This is true because essentially that you can approximate continuous things by smooth things. This is true because simplicial cohomology and singular cohomology are computing the same thing. And this is true because of the first part, that the cohomology is isomorphic. So in fact, we saw this as a theorem that for a simplicial complex, this was true. And when you tensor with that, this is still a quasi-isomorphism. So the point is that this, when you tensor with R, there's a zigzag, so there's no one single map, but at the end, this through a zigzag is quasi-isomorphic to the de Rham forms. So this is not just capturing the Q information, but when you tensor over R, this is also connected to the differential forms, which connects to geometry. Okay, so one expects that we can hope to extract rational homotopy invariants of M instead of obtaining it from here because of this zigzag. Maybe try to obtain it directly from the differential forms. And maybe we'll talk about that in the last lecture a little bit. So, and there's one more remark which people can check. So if you have path connected spaces X and Y, then we have a natural quasi-isomorphism from APL X tensor APL Y to APL X cross Y. And you should think of this in the light of what you do if you had two manifolds M and N, and if you put forms on M, tensor forms on N goes to forms on M tensor N. Well, you have a form on M, you can pull it back to M cross N. You have a form on N, pull it back to M cross N, take the wedge there, and that would be the map at the level of forms. And this is pretty much going to be the same kind of a construction. So the map is natural, and it turns out this is a quasi-isomorphism because of what we have talked about earlier. So, since we're working over Q, the point is you're not losing anything by computing the cohomology of X cross Y by computing it using this, because there's no X terms to deal with. Okay. Yeah, so among the models of commutative cochains for topological spaces, so you have seen one model, which is APL of X. There are probably others, but it turns out Sullivan models play an important role. So let me. So can I take maybe 6 more minutes because I started, I think, a few minutes late. So.
Go ahead, Somnath.
Okay. All right. Yeah. So, okay. So we want to talk about these models because this is probably, and I mean, if you don't get too much into the theory, an easy way of seeing how algebra comes in, and even if you do not know where the algebra came from, it helps you compute things. So we'll talk about what are called Sullivan models. So let's talk about what is a Sullivan CDGA. So Sullivan CDGA is basically a commutative differential graded algebra of the form wedge V comma D. So again, this, if you recall our notation earlier, this is just a free commutative graded algebra. So there's some underlying graded vector space V, and it's the wedge of V, which means symmetric on the V even and exterior on the V odd, right? So the only thing is we have to talk about what this D is, and this D is going to be sort of specially designed. And yeah, the underlying algebra is free by choice or by construction, and the D has this specific property that suppose V is of this form, so there is nothing in V0, it's only from V1 onwards, and I'm insisting on the assumption that V should admit a basis X alpha, and these are indexed by a well-ordered set, and we'll see in some examples that this V is actually finite dimensional, in which case the ordering is almost up for us to choose. So we'll assume that the basis is indexed by well-ordered set such that whenever I take D of X alpha, this is going to be some wedge of certain elements, right? So the point is, so D of X alpha, of course, lies in wedge of V, because D maps wedge V to wedge V. In particular, it maps V to wedge V. But whatever element it lands in the wedges of, those elements can be written in terms of the basis elements, and those basis elements that appear in the expression of D of X alpha should have should be less than X alpha in this order, or so I shouldn't say X alpha. The basis elements that appear in the expression of dx alpha, the indices of those should be less than alpha. Okay. So we'll see some examples. Hopefully this will clarify where this ordering is coming from. Maybe when we talk about the actual Postnikov tower construction of these things in the next lecture, it will be clear why this ordering is coming into play. But take it for what it is for now, okay? So as an example, you can take wedge x comma y. This is a vector space where x is in degree 2. So V is V2 direct sum V3. V2 is a copy of Q. V3 is a copy of Q. That is generated by y in degree 3. And I am putting dx equal to 0 and dy equal to x squared. So dy is x wedge y, x wedge x, sorry. And I insist that x is less than y, or in the ordering x is less than y. And you can check that this is a Sullivan CDG. Okay. In fact, you should observe that this is the cohomology. Also, if you compute the cohomology of this agrees with the cohomology of S2, because if you compute the cohomology, the only thing that survives is x, and x square is 0 because x square is exact, right? So x square is the co-boundary of dy. So this agrees with the cohomology of the two sphere. Same with something like this. You take wedge of x comma y. So x is placed in degree k, y is placed in degree k minus 1. And I'm assuming this is at least 1. And I put dy equal to x, which enforces dx to be 0 because d square has to be 0. And then you can check that such CDGAs are, I mean, the cohomology is that of a point. There's nothing to check. Okay, so x goes to 0, but x is killed, and y, of course, never goes to 0. So the only thing that you get is that. Okay. So yeah, so minimal CDGA is a Sullivan CDGA, which has the property that when you take d of v, so you take any vector in capital V, take d of that, that typically lands in wedge of v, but I'm insisting that that should land in wedge bigger than or equal to 2 of v, which means if I take a x alpha, d of x alpha shouldn't look like x beta plus some other terms. It should look like x beta wedge x gamma, or x beta wedge x gamma wedge x eta plus other terms of the same type. Okay. So this is a slightly nicer condition. So here is an example. You can take wedge of x, y, z, w. X and y are both of degree 2. Z and w are both of degree 3. And you say that dx, dy are both 0. dz is x into y. So dz actually lands into wedge 2 of v. And dy is x square minus y square. This is also x wedge x minus y wedge x. So this dw also lands in wedge 2 of v. So this is a minimal CDG. Okay. Okay. So these are pretty straightforward examples. So the point is, okay, what is the difference between a Sullivan CDGA and a minimal CDGA? Maybe if we need this, I'll talk about this connection in the next talk a little bit. So the point is that there's this algebraic thing that any Sullivan CDGA is basically a tensor product of a minimal CDGA and a bunch of contractible CDGAs. So essentially, given any, so you can take the tensor product of these two, and that is still going to be a Sullivan CDJ. But you see in the cohomology, this doesn't contribute. This contributes a k in degree 0. So it's still the cohomology of this. So, and that is precisely the statement that any Sullivan CDJ is a product of a minimal CDJ with a bunch of things of this kind. Okay. Yeah. So what is a minimal model? Finally, we were able to state this. So maybe I'll state this thing and then stop. So a minimal model for a commutative differential graded algebra is a minimal CDGA of this form with a quasi-isomorphism from this to the given CDGA. So you're simply looking for, so it's called minimal primarily because it's something very tractable and you can compute things with it. So that is probably how I would put it. So you're trying to look for a model with which you can compute certain things. And that means this should be a quasi-isomorphism. So the cohomology of this computes the cohomology of the original CDGA, and this should be minimal. Okay. And the insistence on minimal is going to be clear in a moment, but this is the definition. Okay. So what about minimal models of spaces? Well, a minimal model for a space X is going to be nothing but a minimal model for this particular CDGA, the piecewise linear Q forms. So if I have a minimal model for APLX, I'll call that a minimal model for the space X. Okay. So yeah, so here's a theorem which sort of justifies perhaps a bit of what's going on. So if I have a connected CDGA, this is a terminology probably others will use. So connected CDGA means that the zeroth cohomology is K. Okay, pretty much the same you see in spaces, right? In the spaces you want it to be path connected or connected. So the first claim is there is always a minimal model for such a connected CDGA. That's the first claim. The second claim is if AD is simply connected. So you might say, what is simply connected? Well, simply connected means the first cohomology is 0. So this is analogous to what happens in the level of spaces, but this is an algebraic condition. Then, okay, and this simply means that if you look at hk of a comma d, that's a finite dimensional vector space. That's all. Whenever I say something is a finite type, each of the pieces are of a finite dimension. So if it has this property and each of the hkad is finite dimensional, then the v that you get is also a finite type, meaning each of the vk's are also finite dimensional. So that's what you conclude. And the third thing which helps us sort of talk about this, the minimal model, is that in the simply connected case, which is the assumption in part 2, any two minimal models are isomorphic as CDJs, meaning if you have wedge v comma d and wedge w comma d prime, both quasi-isomorphic to a comma d, then wedge v comma d is isomorphic to wedge w comma d prime. Okay? Not quasi-isomorphic, they're isomorphic. So that is the key thing. Okay? So yeah, so in view of 3, one speaks of the minimal model of a simply connected space. So I'll probably stop here. So there's one more. So the slides are already up. So there's one last slide where I do some examples, but these are pretty straightforward. So I urge people to go back and look at it. If you have questions, we can like discuss it in the discussion, or maybe in the next lecture. But let's stop here. Okay.
Okay. Thank you, Somnath. So there are a couple of small questions in your chat box. Can you see that?
Yeah, just one second.
So the first one is about the is the category of complete DGA is a co-complete or not?
I don't know.
Somnath, I don't think so.
is-
Yeah, because direct sums of rings are not rings, so that's the problem. I don't know how it.
Yeah, but direct sums are not the are not the product. So the co-product is the tensor product.
Yeah, you can take the
And,
tensor product.
Yeah,
so,
tensor
yeah, the
product.
tensor.
Right.
So in fact, it is co-complete. It has to be co-complete. You need to have finite colimits, and finite colimits can be generated by push-outs, and push-outs.
Yes.
And filtered colimits are easy because it's just like taking a union of large.
Good.
So if you have finite colimits and filtered colimits, you have all colimits. It's a presentable category, I think. So it has, it has all colimits and is generated by like a small by all the small objects.
Oh, very good.
I think.
okay.
Also in the homotopical sense, also if you treat it as model category and then you do whatever homotopy colimits, that it's also, I think, co-complete in that sense. I think. Everything.
Yeah, so just to add on, why I asked this question was because we have this APLs defined for simplicials, right? And
Yeah.
you have like these degeneracies and phase map. Why can't you just directly define APL as the co-limit over the element of the simplicial set, like?
Yeah, basically, I think that is what is going on. I mean, in this A construction, that is what is going on, basically. They are just doing it like that.
Okay.
I mean, if you, but for a topological space, it's just better to just use the singular construction or something like that.
Okay, this might be getting late, but finally, the last question is: so this functor should admit a right adjoint because this can be defined in terms of co-limits, say. So, what would be a space given a simplicial CDG or something? Like, is there any interpretation for that? Like to go the other way, what would be the right adjoint to this functor?
I see. No, I don't. Again, I don't know offhand what that would be. I can probably think about it, and if I get something, I'll let you know. I don't know offhand.
Yeah, I think we should continue these things in the introduction session because it's already 6.
Yeah,
it's already 6. So maybe we can start after 4 minutes at 5 past 6, right?